In the past few videos, we've been working towards creating a summing amplifier using a few AC sources. And if I were to run it using a transient simulation, we can see that we still have the same output that we had last time, where we had our sine wave, triangle wave, and square wave. But now I'm going to be adding a bit of complexity by actually adding some filters and then showing you how to use LTSPICE's frequency simulation to validate your filters and make sure they're working properly. And this is good for an example. In this case, let's assume our sine wave is actually coming from an analog source that's external, and we want to filter it to minimize some of that noise. So I'm just going to go ahead and get started by placing down some RC components, because I'm actually going to be making a notch filter, and the components that you're going to see me use in this schematic are catered towards creating a 60 hertz notch filter, because let's assume that we want to filter out some power line frequencies at 60 hertz. And I'm going to be eliminating this VS symbol because I'm going to be attaching it to the end. And so now I'm going to be simply connecting all of these components together using the same tool I've already shown you. And now I'm just going to add some grounds. So as I mentioned previously, I'm going to be creating a 60 hertz notch filter, so these component values will reflect that. So 2.7 microfarads here, and then another 2K hertz, and then this is 1.33 microfarads. This is 1 kilo ohms, and this is another 1.33 microfarads. And to minimize any effects of loading, I'm going to be adding a voltage follower or voltage buffer, however you may kind of know that circuit, which is simply consists of a op amp with the negative feedback tied to the output. And so I'm going to be connecting this to output, and there we go. And because I already have voltage power sources here, I'm just going to be copy pasting the same power supplies because I want them to share the same power supplies. There's no need to make them separate in this case. And then to make sure that the output of this filter is still connected to the input of our summing amplifier, I'm going to be connecting the output of this op amp to VS. So in this case, I'm going to be extending it from here and then copy pasting VS here. Alrighty, so now we have a basic filter, and now I'll be showing you how to actually run a frequency simulation. And to do that, we're going to be using LTSPICE's .ac command, and I'm just going to be writing it here, where .ac actually refers to frequency simulation, because we're going to be running an AC analysis. It's similar to the DC sweep, but in this case, it's actually .ac instead of .dc, where we have the sweep type, the number of points per decade, or per region of frequency that we're going to be measuring through, and then as well as the start and end frequencies. And again, you can go to the simulate section on your toolbar, above your toolbar, and go to edit simulation command and simply go to AC analysis. And from there, you can get the same syntax that I've shown here, but with a bit more pick and place scenarios to make it a bit easier, especially if you're not familiar with the syntax. And so here you can choose between octave, decade, linear, and list. And again, with list, you can simply type in the frequency ranges or frequency values that you want to sweep through. And for this example, I'll do it using the simulation command. I'll do decade, where I type in DEC. And then points per decade, I'm going to be choosing 100. So what this essentially means is that if I'm sweeping from 1 hertz to 10 hertz, I'm taking 100 points in between 1 and 10. And then if I move on to 10 and 100, I'll be taking 100 points in between there. It's a great way to get that really nice, smooth version of your signal. And the more points you have, obviously, the longer the simulation takes to run. But I found for basic filters, 100 points per decade seems to be a good enough compromise to give us the nice curvy output of our filter without compromising long wait times, as well as a start and stop frequency. And so here is where I recommend actually finding the cutoff frequency of your filter and going to magnitudes above and below that. So in this case, I know I'm running a 60 hertz notch filter. And so my cutoff frequency is going to be 60 hertz. And so I would like my start frequency to be at least 2 magnitudes lower, so 0.6 hertz. But for this example, I'm going to be going even lower and going to 0.1 hertz. And for my stop frequency, I'd like it to be 100 times larger than the cutoff. So in this case, my cutoff frequency is 60 hertz. Ideally, I'd like to go at least 6,000 hertz, but for this example, I'm going to go way above that and go to 100 kilohertz. And this is because we want to be able to capture the wide changes in our signal, as filters don't necessarily change that much with small increments in frequencies. It changes a lot with large frequency ranges. And so by choosing magnitudes higher, 100 times higher and 100 times lower, we're able to get the full characteristics of our filter without having to worry about missing out on any important details. So with that, I'm going to be clicking OK. All right, so now after you specify your SPICE simulations, one thing we also have to do is actually specify our voltage source. Otherwise, you're going to run into an error saying your voltage source was unspecified. And to actually specify a voltage source, simply right-click on the voltage source you want to run a frequency sweep on. And this time we're actually, instead of going through the functions tab, we're going to be looking at small signal analysis. So how LTSPICE runs an AC simulation is that it outputs a sine wave of a specified amplitude that you specify in the small signal analysis section, along with a specified AC signal phase. And it does this at various frequency points, measuring the output, and then finding the gain, so the output over input ratio at each of those frequency points to calculate, one, the decibel log gain, which it can then use to plot. And that's how you get something called a Bode plot, which essentially plots gain over frequency, which is characteristic for any frequency simulation software that you actually want to run. That's how you characterize your filter. And so we'll be able to see how the output of our filter changes with respect to frequency. That is, what frequencies we're attenuating our signal and at what frequencies we're letting signals pass through. And so for this example, I'm going to be choosing an AC amplitude of 1 and an AC phase of 0. I'm going to click OK, and as you can see, it shows up here. And notice how we're actually not setting up any functions. We're not setting up any transient functions here. We're only focused on the .AC or AC signal analysis. And so now if I click Run, we can see that if I click the output of VS, we can see that we have a characteristic notch filter where we're only filtering out a certain frequency. And we're based around 0 decibels, which makes sense because there's no gain involved. We'll get to that later. But if we take a look at our cursor and hover over the very tip of the circle, as we can see in the bottom left corner, our x-coordinate is at 59.5 hertz. So it's close enough to 60 hertz, indicating that our filter is working properly. And so this is the characteristic output of your notch filter. And now if we take a look at the output of our summing amplifier, we'll see that we actually have a very similar output. In bold is the magnitude, where this is how the ratio of our output over input changes with respect to frequency. And in the dotted line, we actually have our phase. So how our output is delayed relative to our input is also characterized by the Bode plot here when you run your frequency simulations. And so here we can see that we actually have a gain that's slightly above 5 decibels, and that's because our summing amplifier has a gain of 2. And if you take 20 times the log of 2, you actually get 6 decibels. So if you convert your gain into decibels, you get 6 decibels, which is why we have a 6 decibel gain over here. But as you can see, our notch filter is still working properly at about 50, 59, 60 hertz. And so we can kind of confirm that this filter is working to our expectations. Alrighty, and so that's how you essentially run a frequency simulation in LTSPICE. And one of the last things I wanted to highlight was the fact that I really encourage you to choose the right start and end frequencies by making them large and small enough to capture your signal entirely. So my rule of thumb, the way I've been taught, is always 100 times smaller and for your start frequency, and 100 times larger for your end frequency. That way you're really capturing the nice characteristics of your filter. But that's essentially the basics of running a frequency simulation in LTSPICE. And if you want to change the axes, so let's say you don't want a Bode plot, you can actually right click on the left vertical axis and change to a Nyquist filter, which gives you a Nyquist plot with respect to the real and imaginary components of your signal. And you can even go to a Cartesian plot as well. And with that, that's essentially the basics of running an AC simulation.